Hello, class, and welcome to Chapter 6, Section 3. This will be the final section in our Chapter 3 discussion on the periodic table, and we'll jump right into this talking about periodic trends. So we've been learning a lot about the periodic table, how it's laid out, and we'll kind of dive more into the periodic trends now. So periodic properties are characteristics that all elements on the periodic table share, and group trends are patterns in a property as one reads down a group. So there's two factors that affect group trends: attraction between the nucleus and the valence electrons. As the energy level increases, it increases the distance between the nucleus and the valence electrons, which weakens their attraction, as well as electron shielding, where the inner shell electrons will block the attraction between the nucleus and valence electrons. So we can see here how each circle represents an energy level, and as energy levels are added, the distance between the nucleus and the electrons increases, which will weaken the attraction between the nucleus and those valence outer shell electrons. A period trend are patterns in a property as one reads across a period, across a row, and one factor that affects period trends are that as one reads across the period, the number of protons increases from element to element. So this increases the nuclear charge, thus a stronger attraction for those valence electrons. So look at the period trend in this way. As the positive charge increases by adding a proton from element to element, the attraction between the electrons and the protons is much stronger, pulling the electrons closer to the nucleus. And for each property, think about how this attraction is going to affect the property. The atomic radius. So this is half the distance between two adjacent atoms. It gives you the size of the atom. That's what the atomic radius refers to. Across a period, the atomic radius trend decreases. And why? Because the nuclei have a greater nuclear pull, a larger positive charge, which pulls electrons closer as we move across the period, across a row. So we have more nuclear charge, for example, in chlorine, positive 17. So the electrons are pulled closer to the nucleus, and there's a decrease, a lower or smaller atomic radius, whereas aluminum has a higher atomic radius because it has a less atomic charge and the electrons are not as attracted. The trend in atomic radius is the atomic radius tends to increase when you move down a group. And why? The greater number of energy shells. So as we add on energy shells, as we move down a group, we are increasing that atomic radius. So for example, going from lithium to sodium to potassium, we're adding energy shells, so we're making the atomic radius larger. So you can see here, in general, this is something you want to learn and be aware of. The atomic size or atomic radius decreases moving across the period, across the row, but the atomic size increases when you move down the group, when you move down the column. More about periodic trends, recall reactivity. So in terms of reactivity in metals, reactivity decreases across the period and increases down a group. And the reason for this is the larger the atom, the weaker the nuclear pull, and the more easily electrons are lost and the atom becomes stable. In nonmetals, reactivity increases across a group and decreases down the group. And for the reason for that is the smaller the atom, the greater the nuclear pull and the more easily the atom attracts electrons. Some compounds are composed of particles called ions, and an ion is an atom or group of atoms that has a positive or negative charge to it. And an atom is electronically neutral because it has an equal number of protons and neutrons. So for example, an atom of sodium has 11 positively charged protons and 11 negatively charged electrons. So those cancel each other out, and that is neutral. So the net charge on sodium is 0 because positive 11 cancels out with negative 11 to be 0. So it's electronically neutral. If we have a positive or negative ion, this forms when electrons are transferred between atoms. Atoms of metals, such as sodium, tend to form ions by losing one or more electrons from their highest occupied energy level. For example, in the sodium ion, the number of electrons, 10, is not equal to the number of protons, which is 11. Because there are more positively charged protons than negatively charged electrons, the sodium ion has a net positive charge, and we write that as Na positive because it has a net positive charge. And this will be really important if you ever study human biology. You'll notice that sodium ions with their positive charge are the whole reason why our nervous system works. So continue studying this if this interests you. So an ion with a positive charge is called a cation, and the charge for a cation is written as a number followed by a plus sign. So if the charge is 1, the number is 1 plus, and it's usually omitted from the symbol from the ion. So for example, sodium 1 plus would just be written as sodium positive, standing for 1 plus charge. We have other ions that will have a 2 plus, and then we'll include that number 2 when we're writing that superscript. Atoms of nonmetals like chlorine tend to form ions by gaining one or more electrons. So in a chloride ion, for example, the number of electrons, 18, is not equal to the number of protons, which is 17. So because there's one more negatively charged electron and positively charged proton, the chloride ion has a net -1 charge. And you can see that there, and we write it Cl negative for chloride ion. And again, we would add in a 2 or a 3 if it was not 1, but usually when it's just a 1 negative, like the 1 positive, we just omit the 1 and it becomes negative or positive. So an ion with a negative charge is called an anion, and the charge for an anion is written as a number followed by a minus sign. And I have a little visitor with me who's staying very quiet. Ionization energy. This is the energy required to remove the most loosely bound electron from a gaseous atom. Across a period, ionization energy increases because the stronger the nuclear pole makes it more difficult to remove those electrons. So the ionization energy increases, and you can see that here. There's a greater nuclear charge, so there's a greater ionization energy in chlorine, for example, because it takes that much more energy to pull those electrons away because they're that much closer to the center of the nucleus. Ionization energy, though, decreases down a group because larger atomic radiuses means less nuclear pull, and it's just easier to pull away those electrons from those outer shells. So the larger atomic radius, less ionization energy, easier to pull those electrons away, whereas the smaller atomic radius, more ionization energy, more energy required to pull those electrons away. Ionic size. So during reactions between metals and nonmetals, metal atoms tend to lose electrons, and nonmetals atoms tend to gain electrons. And this transfer of electrons has a predictable effect on the size of the ions that form. Cations are always smaller than the ions from which they form because they're losing an electron, so they're becoming smaller, whereas anions are always larger than the atoms from which they form because they're gaining an electron. All right. Ionic size tends to increase from top to bottom within a group, and the size of cations and anions will decrease from left to right across a period. Group trends in ionic size. So for each of these elements, that ion is much smaller than the atom. The radius of the sodium ion is about half the radius of a sodium atom, for example, because the sodium is losing electrons, so it becomes smaller. When a sodium atom loses an electron, the attraction between the remaining electrons and the nucleus will increase, and as a result, the electrons are drawn closer to the nucleus. Group trends in ionic size. Metals that are representative elements tend to lose all their outermost electrons during ionization. Therefore, the ion has one fewer occupied energy level. The trend is the opposite for nonmetals like the halogens in group 7A, for example. So for each of these elements, the ion is much larger than the atom because they are gaining electrons. So for example, the fluorine ion is more than twice the radius of a fluorine atom. And as the number of electrons increases, the attraction of the nucleus for any one of those electrons will decrease. So from left to right across a period, two trends are visible. A gradual decrease in the size of positive ions, cations, as they are losing electrons, they're becoming positive and becoming smaller. But a gradual decrease in the size of negative ions because those are anions. So here is the trend in ionic size moving across the periodic table. So this is just a great look. The size of cations decreases in this part of the periodic table, and the size of anions decreases in this part of the periodic table as we're moving across. And the size generally increases as we're moving down the groups. Electron affinity is the energy associated with the addition of an electron to a gaseous atom. Across a period, electron affinity increases because the stronger the nuclear pole makes it more easier to attract electrons, as shown here. The greater the nuclear charge, the stronger the nuclear pole, it will attract electrons. So electron affinity increases across the periodic table. But it tends to decrease down a group. The larger atomic radius means less nuclear pull on those outer electrons, so electronegativity decreases down the group. The electronegativity then is the measure of the attraction for electrons, where fluorine is actually the most electronegative. And the closer an atom is to fluorine, the higher electronegativity is. And it's a scale of 0 to 4. And fluorine is the most electronegative, meaning it has the biggest attraction for electrons. Across a period, electronegativity increases. The stronger the nuclear pole makes it more easier to attract electrons, as shown here. But moving down a group, electronegativity decreases because the larger atomic radius means less nuclear pull on outer electrons. So here's a summary of trends, and I would encourage you to just take some time and make sure you understand these summaries well. If you're with me in the year-long chemistry course, we're going to move into this more, and understanding these trends will be really helpful as we move on to following chapters. Thank you for listening, and we'll see you for the next chapter in the next semester. God bless your